Hello students, in this problem we're going to transform the diffusion convection equation into the heat equation. So I'm going to look for a way to eliminate this minus V Ux term. Now if you did not take a look at the transformation of a PDE, the uninsulated case, I recommend that you stop here and you go to that case first and look at that one. We're actually going to rely on that video later on in this one. Also, it gives you a feel for what to expect as we transform this equation. All right, so now we're going to look for a way to get rid of this minus Vux term. Now I'll get into the physical interpretation of this problem in a moment. Let's just do the transformation, and I'll let the procedure of going through the transformation kind of guide our intuition and vice versa. Let our intuition kind of guide the transformation. Okay, so we're expecting either some kind of movement or some kind of loss here, but we can't tell whether or not this is going to be a loss term here because this is a derivative with respect to x. But we expect some kind of movement here because we have velocity in addition to our diffusion. All right, so keep that in mind. We're having diffusive properties, and then we're going to have some kind of movement here with a speed of v. You'll see why that has to be the case. All right, so we have diffusion with that diffusivity. Now remember, that's a decaying exponential, a loss because of diffusivity. And then this we call the convection term, and we're expecting some movement with velocity v. All right, now I'll tell you why we're going to expect some movement here. First, just suppose, let's just ignore the diffusion case, and we end up with just this PDE. All right, now you might recall that we did something similar in the uninsulated case. Except here, instead of viewing this as an ODE, just in respect to time, and then we get the decaying exponential, we can't quite play that game here. We'll just do a separation of variables. Okay, so we just do our separation of variables. Now notice that my separation constant is mu squared, and it's not minus mu squared, and that's because I have a minus v in the temporal term, and I want the temporal term to decay, so I have the minus sign already accounted for. The spatial term, I'm not worried about that blowing up to infinity because that's on a bounded interval. So, and x is not what's going to infinity here. It's t that's going to infinity, or little t. The time is going to infinity. Okay, so I ended up with two ODEs. The first case comes from this one, the t dot minus vt equals mu squared, and I just rewrite that as this ODE and solve that, and we just get a decaying exponential as expected. And then we solve the spatial part, and we get a similar case here, but we have an exponential e to the mu squared. Now, once again, I'm not worried about this blowing up because I'm going to be on a bounded interval. Okay, so I combine those two terms, and I get something like that, but I can't solve for the separation constants. I'm going to need to work that out a little bit later. Also, I want you to notice here the x minus vt. This would be a shift in the spatial coordinate to the right if v is positive, and you would keep multiplying as time was ticking. You just keep moving to the right. So that's what this translation is doing to our heat here. Okay, and that has nothing to do with the diffusivity, with the diffusion. Okay, this is just the movement part, right? We were ignoring the diffusion, so that's why we expect there to be some movement in our heat term here, and that's what this term accounts for. Okay, so in ignoring the diffusion, we just get movement here, and we get a translation to the right with velocity v. All right, now that inspires this transformation, right? So we want to hit this with this exponential. So just like we did in the last video, we instead of hitting with an e to the minus beta t, we hit it with an exponential mu squared x minus vt times w. And this w is going to be our a variable when we transform this into the heat equation. So that'll be our dependent variable. Now, if I do that, okay, so let's plug that into the PDE. So here's my transformation variable. Now, the reason I'm doing this is, for one thing, I need to solve for this mu squared. I need to figure out a way to set this mu squared equal to something so that I get rid of this term here. Okay, so let's just do that. So I take the derivative with respect to t here. This is just the product rule. So you may want to pause the video and work that out for yourself. And here I just factored out the exponential. Then here I had to take, since I do have x dependence in the exponential transformation term here, I do have to take derivatives with respect to x of the exponential and derivatives of w with respect to x here. So the product rule leads to this term here on the left. And then I have a minus v times ux, and I have to do a product rule there. So this is the derivative of the exponential with the minus mu squared v, and then here I have the derivative of the w term, just the wx times the exponential. Okay, so you might need to pause that and work that out for yourself and check your answer with me. Okay, so I'm going to cancel out all the exponentials, and then I'm going to cancel out the terms that are common on the left hand side and the right hand side. And I'm going to clean this up a little bit, and I'm left with this equation here. Now, this equation is going to help me determine what I need to do to get rid of this wx term. Now you're saying, wait a minute, what about this term here? Well, don't worry about that one. We actually know how to get rid of this. Remember from the previous video, this is the uninsulated case, right? We actually know how to get rid of this. We're going to set this, we're going to end up multiplying this thing again by a e to the d mu to the fourth, okay, whatever the mu is. Okay, you'll see that. So we already know how to eliminate this term. It's this term we don't know how to eliminate, and this we want to get rid of, but this tells us what we need to set mu equal to, or mu squared equal to get rid of this term. We set mu squared equal to a number such that this coefficient here is 0. So let's just figure out what that is. So we know how to eliminate that term. That's the uninsulated case, or insulated case, however you want to look at it. And we want that term in parentheses to be 0. Okay, so that term in parentheses is 0 when mu squared equals v over 2d. And so if I let mu be v over 2d, then mu to the fourth is v over 2d quantity squared. But this we know how to get rid of. So you could actually, at this point, stop and then come up with a second transformation to get rid of this term, using the insulated or uninsulated case. Or you could just keep going for it and multiply this by another exponential that will get rid of this term. So let's just go ahead and do that. Let's go for the whole enchilada here, okay? So you've gotten that far. So this transformation gets you this far. But if I just multiply this by the e to the v squared over 4d, because this is v squared over 4d, then I get this transformation here, because I collect like terms, and that gets me down to this equation here. So you could do it in 2 steps, or you can just hit it with 1 step here. And you just have to be a little brave here and do that. Now, let me show you what this looks like. Imagine you have a point source with some heat, and let me bring this up. Here we go. So remember we had the heat, and the heat's diffusing. It's actually moving downward. You can see this peak is actually getting smaller, but it's also moving to the right. So you can see the diffusion happening, although slowly. Okay, this is decreasing, and it's also moving to the right. So that is what convection diffusion looks like. Okay, and I can also look at another case that might be instructive. So just give me a moment here to change my case. And this one's actually kind of fun. So here you have, it's a hot part, or highly concentrated part, and here you have low concentration. And then you're going from low concentration to high concentration, and you're moving to the high concentration case with this velocity. So this is diffusion convection as well. Okay, I'll stop there. So I'll go back to this case, and there's all the mathematics, and that's how you can transform the diffusion convection equation into something that looks like the heat equation, and then you can solve it using separation of variables. All right, good luck.